All right, today we're going to tackle a real classic from the Irodov physics book. Now, on the surface, it looks pretty simple, but trust me, it's this brilliant little puzzle about rotation and forces that really makes you think. So let's just dive right in.
Before we even look at the official problem, let's just try to build some intuition here. Picture this. You've got a bead, and it can slide totally freely on a wire hoop. Now, what happens if you start spinning that hoop around a vertical axis, kind of like a top? The bead's not going to just sit at the bottom, right? You know it's going to rise up the side. The real question is, why does it stop? What determines that one specific spot where it decides to settle?
Okay, so here's the official problem word for word. We have a sleeve that can slide, no friction, along a smooth rod that's bent into a half circle. The whole setup is spinning at a constant angular velocity, we'll call it omega. Our mission is to find the angle, theta, where that sleeve finally comes to rest and just happily spins along with the rod.
Look, the absolute first step to solving any physics problem is making sure you know what on earth it's actually asking. So that's what we're going to do. We're going to break down the key phrases and come up with our attack plan.
The most important phrase in that whole description is steady position. This is a massive clue. It's the problem telling us that we're looking for a point of equilibrium. The sleeve isn't sliding up or down the rod anymore. It has found its sweet spot. That tells us we're dealing with a situation where the forces, or at least some of their components, are perfectly canceling each other out.
All right, you knew this was coming. Anytime you're dealing with forces and motion, the absolute best place to start is with a free body diagram. This is where we get everything out on paper and identify every single real force acting on our little sleeve.
Let's build it together. First up, the easy one, gravity. The Earth is pulling down on the sleeve with a force of mg. No matter what's happening, this force always points straight down. Simple. Second, the rod itself is pushing on the sleeve, right? It's keeping it from just falling through. That pushes the normal force, N. And the number one rule for the normal force, never forget this, is that it is always perpendicular to the surface it's pushing from.
Now, I know exactly what you might be thinking. When you're on a spinning ride, you feel like you're being thrown outwards. So shouldn't we draw some kind of centrifugal force pushing the sleeve out? This is probably the number one most common trap in all of rotational motion.
So here's the deal. We are analyzing this problem from the ground from what we call an inertial or non-accelerating frame of reference. And in this frame, there is no such thing as a centrifugal force. It's a fictitious force that you kind of have to invent to make the math work if you're pretending you're sitting on the spinning object. From our perspective on the ground, that outward feeling is just inertia. The real actual measurable forces are pulling the sleeve inward to force it to go in a circle.
Okay, one last check. What about friction? Well, the problem gives us another one of those great little clues. It says the rod is smooth. And in physics speak, smooth is basically code for you can completely ignore friction. So that means we only have two real forces to worry about, gravity and the normal force. That's it. Our diagram is done.
Okay, so we've got our physical setup, we've got our free body diagram. Now it's time to translate all of that physics into the language of math. And you know what that means? We're about to apply the most famous equation in physics, F equals ma.
But wait, before we even write a single equation, we have to sidestep a huge geometric trap. I've seen this trip up so many students. There are two different radii in this problem. You've got the big R, which is the radius of the half-circle rod itself. That's a constant. And then you have the little r, which is the horizontal radius of the actual circle the sleeve is tracing out. And as you can see, that radius totally depends on the angle theta. Mixing these two up, it's a classic mistake.
The good news is we can connect these two with some pretty basic trigonometry. If you just picture a little right-angled triangle inside that half circle, the rod's radius, big R, is the hypotenuse. The radius of rotation, little r, is the side that's opposite our angle theta, and that gives us the key relationship we need. Little r equals big R times sine of theta. This is the equation that connects the shape of the rod to the actual motion of the sleeve.
All right, time for F equals FA. Let's be smart about this and break it into vertical and horizontal components. So vertically, in the y direction, the sleeve is in a steady position, which means it's not accelerating up or down, so the net force is 0. That means the upward part of the normal force has to perfectly balance the downward force of gravity. But horizontally, in the x direction, the sleeve is accelerating. It's not speeding up, but its direction is constantly changing to move in that circle. That's centripetal acceleration, and the force causing it is the horizontal piece of the normal force. So now we've got our two equations, one for the vertical forces and one for the horizontal.
All we have to do is solve the vertical one to get an expression for the normal force, N, and then we can plug that right into our horizontal equation. We'll also substitute the formula for centripetal acceleration, which is omega squared times r, and since we already know r is r sine theta, we can plug that in too. After a little bit of algebra, we can finally solve for the thing we were looking for all along, the angle theta.
So we've done all the math, we've followed the steps, and we have an answer. But in physics, getting an equation is only half the battle. We have to stop and ask ourselves, does this answer actually make sense? Is it physically possible in every single situation? Because there is this fantastic little gotcha moment hidden inside our result.
After all that work, after all that algebra, it boils down to this beautifully simple expression. The cosine of our steady angle, theta, is equal to g, the acceleration from gravity, divided by omega squared times r. So simple.
But hold on a second. We all remember from math class that the cosine of an angle can never, ever be greater than 1. So what happens if we spin the rod really slowly? That would make the omega in the denominator really small, which could make that whole fraction, g over omega squared r, bigger than 1. Our equation would tell us that cosine of theta is like 2. That's impossible. So what does that mean physically?
This isn't a mistake in our math. The math is trying to tell us something incredibly important about the physics. It's telling us that there's a minimum speed required to get this whole thing to work. If you spin the rod too slowly, the horizontal push from the normal force just isn't strong enough to overcome gravity and lift the sleeve up. If that's the case, the sleeve doesn't rise at all, it just sits at the bottom.
So what this problem brilliantly shows us is that there are two totally separate conditions, two different regimes, you could say. First, if that rotational term, omega squared r, is less than or equal to g, you're just not spinning fast enough. The system doesn't have enough oomph to lift the sleeve. The only steady position is at the very bottom, where theta is 0. But if you spin it fast enough so that omega squared r is greater than g, then suddenly a second stable position becomes possible, and its angle is given by that beautiful formula we derived.
So what did we really learn here? It's so much more than just the answer to one homework problem. We've actually built a powerful strategy, a toolkit, that you can use to tackle all sorts of problems in dynamics. Let's just quickly recap it. It's really a 6-step process. 1. Decode the problem. Know what the words mean. 2. Draw that free body diagram, and I mean it, this is non-negotiable, with only the real forces. 3. Pick a smart coordinate system that's going to make your life easier. 4. Apply F equals ma in your component directions. 5. Always be on the lookout for those little geometric traps, like our r versus r. And finally, number 6, interrogate your answer. Step back and ask yourself, does this result actually make physical sense?
And I want to leave you with a final thought to chew on. How would this problem change if instead of a sleeve on a half-circle rod, we had a little marble rolling around inside a spinning, smooth bowl? Would the strategy be the same? Would the answer be the same? Give it some thought. I hope this helped.